Okay, so greetings of the day to all present here today. So I welcome you all to yet another week, fifth doubt clearing session or problem solving session for the course Smart Grids Basics to Advanced Technologies, being taken by Professor NP Padhy and Professor Premlata Jena from IIT Roorkee. I am Swastik Sharma and I am a TA for this course. So last week we started with WAMS, wide area monitoring systems. We went through why WAMS was needed, because technology is always evolving and we can't stay backwards with the kind of technology that we have today, right? So we started with WAMS and then we discussed various how to estimate phases for wide area monitoring system, how to estimate these phases help us estimate frequency and voltages, right? And based on those two quantities we are able to get all the other parameters associated with like line flows or other stuff that is relevant for us to do load flow studies or other power system studies, right? And then we started with digital relays. So we talked about why relays are important. So we need to have protection equipment too, because these equipments are costlier and we have to protect them from surges. And today we'll delve into the microgrids and how to protect this new age smarter grids and why these need protection first of all. So yeah, let's start with today's class. Let me share my screen. Yeah, so okay. So first of all, we have been talking about microgrid since the beginning, right? So I have introduced microgrid several times. So what is microgrid? It's like we have earlier we used to have generation at a separate place, loads at a different place. But now we tend to have generation at the distribution side itself where the loads are being served, right? So we can say that these microgrids are miniaturized version of the traditional grids, right? And because these are miniaturized, so we have generation available as well. So eh, uh, uh, they are coupled with the grid, but they also have individual generating units like PV arrays, wind farms, and then hydro-based generation, biomass generation, and other relevant generations, right? Which are present. So these are called distributed energy resources. So we can generate locally, and we have a point of common coupling where we are connected with the traditional grid as well. So this ensures that we have power available locally as well as from the standard place, like the power grid. So these can serve as a single controllable unit at times, and they define an area which and they operate within an area, right? So they operate within an area and as a single controllable unit. Now, why have generation at the distribution side, right? We used to have these localized generating stations at the transmission side. Why do we feel the need to have it in the distribution side? So these can be attributed to the advantages that they have. So first of all, they make our system resilient. So what do I mean by resilient? Let's say that we have a power outage and we are disconnected from the main grid, right? So in order to serve the load, in order to serve our household loads and other loads that are critical for uh, like hospital loads, so they are critical loads, right? They need to be served at all times because it makes sense because these are some things that can't operate without electricity, right? So to make power systems resilient, these microgrids were focused upon. So earlier they started from small diesel generators and then they shifted to other renewable based resources because these can be easily operated or they can easily be mounted at distribution side. Second thing they offer is sustainability. So most of the generating systems that are connected at the distribution side are greener and cleaner forms of sources of energy. So I'm saying greener and cleaner. I'm not saying they are greenest or cleanest, because uh, production of solar photovoltaics is also harmful for our environment. And then we have other lithium. So we have battery storage, right? So production of lithium, we also harm environment in a way. So these are greener and cleaner form of energy sources, and they offer sustainability to the environment. Third is the efficiency. With the availability of these generating stations at the distribution side, we can serve the load better, right? So as we are able to serve the load better, these can help increase the efficiency of the overall operations of the power systems as well. So these are the advantages that they pose. But what happens is, usually they also have certain kind of disadvantages associated with them, right? Everything has advantages and disadvantages. So let's, before going into the disadvantages, let me tell you. So I already showed what a microgrid is. So they have three kinds of operations. So one is grid connected mode, one where they are serving the power locally as well as being connected to the grid at all times. One is islanded mode of operation, where, let's say, if you can see this figure, I've maximized it for you. So I've taken it from this reference. Feel free to check if you want to. So let's say at the point of common coupling, a trip, so there's a trip and we are no longer connected to the uh, traditional power grid, right? So the main power grid. So the local generation is able to serve the local loads, and this mode of operation is called islanded mode of operation. And they also transition in between islanded and grid connected mode when the trip is reinitialized, or when they are reconnected to the system. So there are three modes. Now, when we have grid connected mode, it's easier for us to manage these resources, right? Because the central controller sits at the central place, right? But when it's islanded, these are localized to different distribution feeders, right? So how can we manage them, and how do we know that a microgrid has gone islanded? Like, there can be certain trips that we don't know of, and let's say an islanding happens. So we need to be able to detect that an islanding has happened, because until and unless we know, we won't be able to quantify if a microgrid is acting remotely or not. So there are few different kinds of islanding. So first of all, let me tell you what. Already told you an islanding, but there is a what you say, standardized definition that ma'am has said in her slides. You can go refer to that. I'll just read it out for you. I have the slide. Yeah. So it's a condition in which a portion of an electric power system is energized solely by one or more local EPSs, though the associated PCCs, which is point of common couplings, while that portion of through the associated point of common couplings, while that portion of an area EPS is electrically separated from the rest of the area of EPS. So that means they are not connected to the grid at all. So yeah, so there are different kinds of islanding too. Uh, so this is a distribution substation shown by this orange box. So we have the sub-transmission connection, which is connected to the bulk generation side. And we have other feeders, some local generation, and we have shown one feeder through an enlarged view. So the whole system is called full substation microgrid, and one feeder based microgrid is called a full feeder microgrid. And in each feeder, there can be multiple feeders, because we have radial feeders in our topology, right? So these radial feeders could have individual customer-based microgrid. Let's say you have an EV, right? Or you have a battery storage. Let's say that, and you have a PV. That's more healthy assumption. You can act as a single customer microgrid as well. And you can have multiple different customers involved in it, and this is called partial feeder microgrid. So you have different kinds of islanding cases, and you have different kinds of microgrids. Let's say this relay, this box is let's say it trips, and it's disconnected from the main feeder. What will happen? This partial feeder microgrid will be in an islanded mode of operation, and you can have single customer based islanding too, right? But this unintended islanding, let's say a trip has occurred and you don't know of this can cause serious repercussions to the system. Now, what What are the serious repercussions? So first of all, one is out of phase reclosing. So what happens? Let's say you were islanded, right? So generally, what happens? Your microgrid has some generation and it has some load, and what may happen is this generation and load may not balance all the time when it's connected to, let's say, a traditional grid. So the load could be more, or and the generation is also more. Once it's islanded, what happens? This generation could be greater than less than your load. And what is the condition that happens when the load is or the generation mismatch is there? Can anyone tell me when generation load mismatch is there, what happens?
Imbalance in the grid.
Yeah. So we have frequency imbalance. So frequency starts deteriorating because we have the generation. If the generation is greater than load, frequency starts increasing, and when we have load greater than generation, the frequency starts decreasing. So let's say you had an unintentional reclosing, right, to the main grid. So what happens due to this unbalancing, the voltage and frequency may not be synchronized at all times. So due to this, you could have different operating frequencies and you can have misaligned voltage peaks. So two main problems: different operating frequencies and some misaligned peaks. So your voltage at microgrid level and the voltage at the point of common coupling may not coincide, right? So that could be harmful for your system because it could cause your system go out of synchronism. So synchronism is something that is very important for an AC based system. So due to this voltage and frequency instability, power quality issues happen. So your voltage sag, frequency div, etc., correspond to the power quality issues, and this unintended islanding could cause these issues. Then grid protection interface. We'll talk more about protection equipment. So in our coming slide, there you will be able to appreciate why grid protection is by unintentional reconnection or an unintentional islanding causes grid protection issues as well. Then inverter controller mode switching. So our inverter so our inverter strategy follows the feedback from the voltage at the point of common coupling, right? So if the point of common coupling voltage of the point of common coupling is not in synchronism with your voltage at your inverter based resource, this could cause your inverter to go out of sync. So that's also something that could cause malfunction to your DR. Then your protective device could malfunction. We'll talk more about this. And equipment damage. Since there are power quality issues, your equipment could damage. So we say that some equipment is based to operate under certain voltages and certain frequencies only, right? So if the voltage issues are there, your equipment could be damaged. And let's say there is an unintentional islanding or an unintentional reconnection. A person working over there, let's say he's trying to uh, do something at for a relay at a different place, and there is a reconnection with the main grid. So that could experience a certain what you say it could have devastating effect to that individual. So it could also cause threat to the personal or the human safety. So this leads to what exactly is the so how exactly we can detect this islanding, because this is very relevant. And in order to be able to tell that a microgrid has gone islanded, we need to be able to first of all detect how it's gone islanded, right? You can't always monitor PCC and tell, yeah, okay, your main grid is connected or it's not connected. So there are a few different techniques. So first of all, let me tell you, whenever your main grid or whenever an islanding happens, there is a difference, as I already told you, difference with the generation and load level, right? So due to this, power mismatches happen in the form of delta P and delta Q, which can be written as P load minus PDER and Q load minus QDER, which was earlier being taken from the grid. So when you were connected to the grid, your grid also supplied part of your reactive power and part of your real power. And once the once your microgrid went once your microgrid was islanded, that amount of power mismatch for a few seconds will be there, right? Before a local brownout would happen. A brownout is something when a part of your loads are switched off. So you need to tell these two quantities to be able to. You need to be able to check these two quantities to be able to tell if your microgrid has gone islanding or not. So usually IEEE has set some standards in IEEE 1547. So I've already told about this standard. So this standard talks about interconnection of DRs with the distribution system. So I would request you to please check. It's available on the IEEE website. I mean, you may or may not be able to connect to it using your uh, college or school Wi-Fi. But if you want to check these standards, do let me know. I'll be happy to send it over to you. So these tell us about. So there are. So yeah. So let's say we got delta P and delta Q. So a power mismatch delta P causes difference in voltage, right? Your voltage starts deteriorating. Sorry, frequency. Not only frequency, it's the your yeah, let's say frequency. And then delta Q causes voltage sag or voltage deterioration. So to check these power mismatches, what you can do is you can check the associated frequencies and the associated voltages. And these can be checked using relays that we talked about last time. Relays help us sense these quantities. How do they? How do these relays sense it? We have already discussed through phasor estimation technique, right? So these relays have certain set points. So they have over voltage rating of 1.1 pu. So for some time, so not all, so all relays don't. So for let's say a fault happens for a very small amount of time, the relay won't trip. It has to experience that fault for a certain period of time before it trips. As there are many transients in the system, if a transient happens, you can't switch off your microgrid just because a transient has happened, right? So the over voltage relay checks for this over voltage rating if the over voltage exceeds 1.1 per unit for a particular amount of time, it trips. Similarly, there is an under voltage set point or rating. It's point sorry 0.88, I guess, per unit. Very bad with numbers. And then we have over frequency and under frequency. Uh, So in the standard, it's basically for US. IEEE is a US organization, so it's for US. So they have 60.5 and I guess 59.3 hertz. So you can check what it's for Indian scenario. I don't have the figure for that. So this is what the set point for the relays are. So So what it does is it checks for this over voltage and this over frequency or this under frequency for a particular period of time before the relay trips and disconnects the DR from the system. Yeah. So so how do you so once you have this power mismatch. Let's say you got delta P and you got delta Q. Still, due to this relays, there is a small region where the relay won't tip even if your power mismatch or the even if real power and reactive power mismatch is there. This region is called non-detection zone. So many studies, many researchers are focusing on how to, because of this time lag, this non-detection zone generally occurs, and this non-detection zone causes it can be harmful. Let's say there is a power mismatch. There has been an islanding, but it won't be able to tell if an islanding has happened, right? So since it won't be able to detect this islanding, what's the fun of using this setting, right? So there is this non-detection zone for which the studies have been trying to remove this non-detection zone or minimize the area of this non-detection zone so that better reliance better reliability could be there for these relays or these uh, uh, what do you say for these relays, right? So we have different kinds of islanding detection techniques. One is passive, the other is active, hybrid, and communication based. So in passive, what we generally do is I'll explain each of these in detail. So we monitor an electrical parameter. So it can be voltage, frequency, uh, impedance, etc., where we check how it's deteriorating, and then uh, we detect if the islanding has occurred or not. Similarly, for active, what we do is we inject signals. So how do we inject signals? It's through IBR, inverter based resources. So when I use a acronym or an abbreviation, just let me know. So I generally use it thinking that people would know it, but yeah, if I don't tell, please let me know. So these inverter based resources, also called IBRs, can be used to inject a signal into the system and then check how how voltage, frequency, or other electrical parameters are deteriorating, and then we can tell if islanding has occurred or not. Then we have hybrid. Hybrid uses both active plus passive techniques. So when we discuss, I'll tell you the disadvantages associated with both of these techniques and why we need hybrid techniques. And then we have communication based uh, IDTs. So we are using VAMs, we are using SCADA, right? So we have communication. So why not? Since the whole thing about smart grid is interoperability, all the devices must communicate with each other. So if the devices are communicating with each other, why do we need to inject something or monitor something if we can just let the devices talk to each other, right? So communication based resources are also there. So first we'll talk about passive islanding detection parameters. So we check voltage, as I told you, frequency, impedance, and phase angles and sequence components. We'll discuss more on this. So checking these electrical quantities and then tell if islanding has occurred or not. So first, islanding detection technique is power quality based detection technique. So in these technique, what happens is in like an inverter based DRs, these work on so these have inverter based DRs. Generally, this is used for inverter based DRs. So PVs, wind systems are generally called inverter based DRs because they are connected with an inverter to the main point grid, right? So these inverter based DRs use PWM technique. So I guess all of you are know what PWM techniques are. Pulse width modulation techniques. So what generally happens is we have a DC, right? We generate a DC, say the voltage, let's say, right? So we generate DC from these wind or PV based resources. Then we use a converter, which is called an inverter, which converts DC to AC. So how do we do it? We use it by the help of switches. So what does switch do? You can reverse the direction in such a way that it starts acting. The DC start looking like an AC. So this generally would be like for half cycle you turn it on, then you turn it off, then you turn it on, then you turn it off. Like so, this seems like an AC circuit. Sorry, this seems like an AC voltage, but what's wrong with it is that it's deteriorated in power quality. So there are different PWM based techniques. There are space vector modulation based techniques. Then there are other triangular based techniques. So I don't want to delve into that. So these generally use pulse width modulation based techniques to convert DC to AC, right? And these are already deteriorated. You already have harmonics because of the use of power electronics, right? So what you do, you check if when an islanding happens, the power quality is further deteriorated. The magnitude of harmonics in these waveforms is increased further because of islanding. So you measure the amount of power quality associated with these output of these inverter-based resources to check if an islanding has occurred or not. Then you have impedance-based detection parameters. So what is it? Yeah. So in an impedance-based detection, I forgot adding the figures. Let me the figures. So, hmm, hmm. So what happens is when you are connected to the grid, you see what you see is you see a different this you see a different amount of impedance to the path of your DG, right? So there is this impedance due to the grid. But once it's islanded, what happens? The impedance due to this grid is removed. So when if you monitor the impedance of the impedance that the the DG station is experiencing, you will be able to tell if an islanding has happened or not, right? Then we have rate of change of frequency, or also called as ROCOF. In rate of change of frequency, you monitor how your frequency is changing, right? So I already told you that there is a mismatch, right? So due to a mismatch, your frequency will change. And if you monitor ROCOF, which is so this is an index given by delta F by delta T. So you can use those frequency monitoring techniques I told about in the last class. These were, can anyone tell me what the two frequency monitoring techniques were in the last class we talked about? Anyone? Yeah. Okay. So we talked about zero crossing based techniques, and we talked about phase angle monitoring based techniques, right? So if you use those techniques to monitor the frequency, change in frequency, by getting this index, you can check how the rate of change of frequency is happening. Monitoring that, you will be able to tell if your grid has gone into islanding or not. Microgrid, sorry. So, but it has a few drawbacks. So I won't tell how these drawbacks came. Ma'am has given a case study in her class. I appreciate if people will check that. So one drawback is there is a 15% power mismatch. So that is it won't so it, sorry, I won't say 15%, I will say requires. So what does this mean? That it can only measure once the power mismatch is greater than 15%. So that means it has a non-detection zone, right? So that means relays working on ROCOF, or rate of change of frequency, won't work until and unless a power mismatch greater than 15% has occurred, right? Then also let's say if you have different kinds of loads, right? Different loads and generations. So frequency is a parameter which is generally affected by the inertia of the system. So what is inertia of the system? Let's say your real power goes down pretty quickly, right? The generating station, the synchronous generators present in the generating station, these are rotating at a very high frequency, right? So these have inbuilt, what you say, uh, these have inbuilt inertia, which reduces the amount of rate of change of frequency to some extent, right? Because they are able to supply the extra amount of power back to the load. So this causes what does it do is that this causes the rate of change of frequency to not be too extreme. So, but the non-power electronic based loads, if they are non-synchronous based DERs, these won't have that luxury of inertia, right? If they don't have the luxury of inertia, what would happen is this rate of change of frequency will be affected. And it can be extreme, it may not be extreme, it may not be able to tell if the islanding has happened or not. So this is one part of it. Then, uh, okay, then you have rate of change of voltage phase angles. So if your voltage phase angle, not just voltage phase angle, also the current phase angle, if they are changing, so you will be able to tell if islanding has happened or not. So it's called ROCPA, the rate of change of phase angles. It's given by the phase angle difference between voltage and current. So if you monitor this rate of change of phase angles, you will be able to tell if your microgrid has gone into islanding or not. Now, in all of these islanding techniques, one thing was missing. What was it? You were waiting till the time your system went into, let's say, your system was behaving differently. So until and second of all, rope off the rate of change of frequency, it requires at least 15% power mismatch to be able to tell if islanding has happened or not. So these techniques wait for the system to go into these wait for the system to go into islanding, and after that still takes some amount of time to tell if the islanding has happened or not, right? So these are slow acting techniques. So what we do is we shift to a more active based islanding techniques called active islanding detection techniques. So what do you do in these techniques? You inject signals. So under a signal injection based technique, what you do is you have inverter based resources, right? So what you do, so this is your converter or the inverter based resource. So you inject a disturbance into the system. Let's say you inject the disturbance as I disturbance. So once you inject this disturbance, you check uh, how your system responds to this disturbance. So what generally happens is, so in these techniques, so you inject some low frequency or a high frequency signal. Generally, we inject low frequency signal, and you wait for the behavior, this behavior at this PCC, and then you check if this behavior corresponds to something that could be caused due to islanding or not. But how do you tell it? So can you, so what you do is the 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 grid generally has, yeah, so this grid generally has lower impedance, and your load generally has a higher impedance, right? So your disturbance and the harmonics injected by your system, because you're injecting disturbance, there will be associated harmonics as well. These are absorbed by the main grid, and what you have at your load end is 60 hertz or 50 hertz current, which is being fed to the loads. But under point of when the system is not connected to the main grid, what happens? This disturbance is also teletransported to your load. So if you measure what is happening at your point of common coupling, you will be able to tell if uh, if islanding has happened or not. So still in this system, what you're doing is you are waiting, you are indirectly causing your system to go out of you go out of synchronism, or you're causing the system to go into disturbance, right? So and you're harming, and you're also creating a power quality issue. And so these injection techniques also don't what you say, these also don't uh, appreciate, or they cause the system to go under what you say, stress, to be able to tell if an islanding has happened or not. There is one more technique called positive feedback technique. No, no. Under the same active islanding technique, detection techniques. So in this positive feedback based technique, what you do is, so you check for the electrical quantities like frequency, phase angle, voltage deviation, etc. So how you do is you check if you check these as a feedback to the system. So what you do is, so your inverters have generally they take feedback from voltage at PCC, right? So what you do, you you take, apart from these voltages, you also take the frequency, phase angle, and deviations as a positive feedback to your converter to tell if so what it does under islanding, it will start behaving differently as opposed to how it does when it is connected to the main system. So this causes the DERs to operate unstably, right? Because you are injecting a feedback which wasn't designed for your system, right? So once you are able to tell if your DR is behaving in an unstable way, you will be able to tell if the islanding has happened or not. So still, in these active islanding detection techniques, what is happening is you are waiting for your system to go into, let's say, an unstable region, or you're causing it to go into an unstable region. So these are some of the limitations. So these are some of the limitations of these active base techniques. So let me briefly summarize so that all are on same page. So we'll talk about both active and passive. So the first of all is we cause a power quality degradation. Sorry. Yes. So we cause a power quality degradation to happen, right? We are injecting, we are checking if the impedance has changed, frequency has changed. So it's causing it to go into uh, uh, a degraded power quality. Second, um, you have a non-detection zone, right? Third, it's uneconomical. So if you have power quality issues, what you do, let's say you have voltage sag happening, if you have current frequency deteriorating, you use SVCs or different what you say components which help in improving the voltage and frequency, right? So these cost to these are cost to the operator. So these are uneconomical as well. So because you're causing it to go into unstable, act unstably, and then you have to improve the power quality as well, right? So it's uneconomical as well. So to be able to so to able to address these limitations, two different aspects were proposed. This one came directly from IIT Roorkee. So this was proposed by the research group at IIT Roorkee under Premlata ma'am. So what they did was they checked the rate of change of superimposed negative impedance. So first of all, I would like to ask if everybody knows what is negative sequence, positive sequence, zero sequence. So if anyone who doesn't have an idea, please let me know. I can uh, tell you about it. Anyone?
So can you give a brief review?
Okay. So
Explain the polyphonic sequence.
okay. So what happens is your distribution systems are unbalanced, right? So what causes this unbalance is because your loads are connected in one phase, two phase, and sometimes they are connected in three phase as well, right? So this causes the voltage, current, and other things to be out of sequence. So if they are out of sequence, what happens is they may not be same in magnitude, and their phase angles, which should be 120-degree apart, won't be 120-degree apart, right? But in order to be able to, so this unbalancing, right? So what you do is, instead of uh, checking unbalanced systems. So if you, instead of checking unbalanced three-phase voltages, what you do is you create a symmetrical components of these three-phase voltages. So what are these three symmetrical components? You decompose these unsymmetrical, unbalanced voltages and currents into three components. One is positive sequence, second is negative sequence, and third is zero sequence. So what generally happens is, so these positive, negative, and zero sequence tell you if your system if your system is if these exist, if positive, negative, and zero sequence components exist, that means your voltage and current calculations are unbalanced in nature. So what is this positive sequence? So in positive sequence, they follow the same phase rotation of your normal what you say ABC phases. So what is the normal phase rotation? So they are placed 120-degree apart, right? So this is VA, this is VB, and this is VC, right? And in negative sequence, it's just that the phase rotation is replaced. Instead of ABC, it's ACB. So it would be something like this. So I can just copy now. Yeah. So these are VC and VB. And zero sequence, they don't have any phase angle associated with them. So this is VA. So decomposing them in three different components help us in analyzing them in a single phase perspective only, right? Because since they are balanced components, but there are three different quantities, right? So how do we denote it? So to get the original thing, this positive sequence component is denoted as VA plus AVB plus A square VC, where A is EJ 2 pi by 3.
Sir, may I ask one thing? Sorry for
Yeah,
interruption. May
no,
I
no,
ask
no.
one thing?
Yeah.
Sir, in positive sequence, we take the order like in clockwise, like VA, VB, VC in clockwise rotation,
Hmm. Hmm. But
and it's in
okay,
anti-clockwise. No.
no, no, no. So in so A, just tell me. So what is the phase angle between A and B?
Basically, I think alpha.
Huh? Alpha 120-degree, right? So
Yeah, 120.
B lags A by 120-degree. So I've shown B lagging A by 120-degree, and in the C side leads A by 120-degree. I think this is correct. Does anyone have any issues? Can anyone check if what I've written is correct or wrong? I think this is correct.
Yes, sir, correct. What I'm asking, sir,
Hmm.
for priority sequence, we take the vectors in clockwise, like clockwise direction.
Oh, you're talking about rotation. Yeah, yeah, yeah. The clockwise.
Yeah, yeah.
So this, yeah, yeah. The rotation. I haven't shown the rotation, but this rotation is like this only, and this is something like this because you want to get A, B, C component, but in this the rotation is anti-clockwise. The A, B, C component is rotating anti-clockwise in negative sequence. I don't know what exactly your question is. Can you
Yes, sir.
please
Now, okay.
elaborate?
Regarding rotation
Yeah, yeah.
sequence.
The rotation is clockwise in positive and anti-clockwise in negative, but you can check it how the A, B, and C phase components are displaced from each other. Once you get that, you will be able to tell how the rotation is happening, right? So
Yes.
here, yeah, yeah. So
Thank
yeah,
you, sir.
no, no, no. So don't thank me. I mean, you can interrupt me anytime. So negative sequence is denoted by V2, which is simply VA plus A square VB plus A VC. right? So this is how you denote your positive and negative sequence components. So these sequence components tell us if an unbalance has occurred in your system or not. And these are crucial with respect to distribution systems, because distribution systems are mostly unbalanced. Right? Sorry, my throat is itching. So yeah. So so you have so what you do is they were checking, since there will be an unbalance in distribution system, so they directly took the negative sequence component and they checked how much it was displaced from its post and pre position. So post means post islanding and pre islanding. So they superimposed it by subtracting from each other, and then they saw how it was varying with time, with respect to time, and then they constructed a index based on that, which was called rate of change of superimposed negative impedance index. And this showed under, you can check ma'am's slide. She has some 3 or 4 case studies which showed that it was working much better than Rokoff or ROCPA. But this is still a passive islanding detection technique, right? But it was able to, but it does not have the drawback of 15% power mismatch. It does not, it can detect under 15% as well, right? Similarly, let's move further. So now we talked that there are limitations associated with active and passive IDT, right? So we went to, so in order to evaluate them perfectly, we took the advantages of active and the advantages of passive, and we created a hybrid islanding techniques. So here also I showed at zero power mismatch, it is difficult to detect islanding conditions since electrical variation is less. They drive islanded system into unstable mode or degrade power quality. But in hybrid islanded detection technique, what you do is you monitor the system using a passive islanding detection technique, and then predict by using an active islanding detection technique, right? And by this way, you can significantly reduce your power quality issues, and you have a better detection capability than the passive IDTs. So how do you do it? There is one way. You measure the voltage unbalance. Now, what is voltage unbalance? It's the ratio of negative sequence component of voltage to positive sequence component of voltage. So you measure this voltage unbalancing, and then you measure, you use it as a set point for frequency. So how do you do it? You monitor it. You check if it is over the acceptable limit. Once it is over the acceptable limit, you set the DG's frequency from 60 to 59 hertz. Why do you do this? So what you are doing here is you are injecting instability into your DER's operation by reducing the operating frequency. And then you check, after monitoring it for 1.5 seconds, you check if the frequency is below 59.2 hertz or not. So you change the feedback of your DG from 60 to 59 hertz. And if the DG's frequency goes below 59.2 hertz, it sends a trip signal, and you are disconnected from the PCC, and your frequency set point is then restored to 60 hertz. If not, it is still restored to 60 hertz, and then you can work with the being connected to the grid as well. So this part is active IDT, and this part is passive IDT. And in this way, still you are deteriorating your power quality, but not too much. Then you move further. So there are communication based detection techniques. As I've told you, so the main focus of smart grid is for the equipments to communicate with each other. It's the interoperability, that is communication with the systems at all times. So so how are you doing it? It's through communication protocols. So there are 4 different kinds of communication based detection techniques. One is power line carrier communication. So what you do, at the behest of your PCC, you have one transmitter and receiver, a transmitter and receiver. Once there is a trip signal, your PCC is opened and the transmitter conveys this to your receiver. And then your receiver changes the set point of the PV inverter to perfectly match the load changes, right? Sorry, to match the generation changes. So this is one way in which your power line communication could help in detecting islanding or conditions where islanding is required. Then you have signal produced by disconnect. It is similar to power line communication. It's just that you use microwave links instead of other communication links, and it's bit expensive. Yeah, someone's mic is open. Someone wants to ask a doubt or something.
Yes, sir. Sir,
Uh,
PCC. What is PCC?
it's the point of common coupling. I've repeated this term. So it's the point at which your microgrid is connected to your traditional grid or your main grid. So it's called point of common coupling. At this point, multiple different microgrids are connected to your main grid because it's a huge system, right? So, so SPD works in the same way. It's just that it uses a different transmission interface. Then you have SCADA. So we know SCADA monitors all the RTUs, right? So if it models all the RTUs, it can also monitor the working of all the different relays or circuit breakers, right? If it can monitor these circuit breakers, it can convey to the operator if an islanding has happened, if the circuit breaker is, let's say, open or not. So this is how SCADA-based system works. Similarly, we talked about it last time, how SCADA sends message only 1 to 2 seconds, right? But now you have synchrophasor based measurement unit, which is synchronized with UTC, which is coordinated universal time. So these convey uh, phasors associated with voltage and currents at all times to all the to the phasor data concentrator, which is connected to uh, your central operator or controller, right? So So by using PMUs or synchrophasors, what you do, you monitor the phasors associated with the buses that it is connected to, right? So and these convey these data to this relay as well. And this relay can monitor the changes in these two different quantities. So so this quantity will be different, will obviously be different when islanding will occur, right? Once it identifies that these two quantities have changed viciously, they will open the circuit by engaging the relay, right? So that's how communication based detection technique, irrespective of the fact that you don't have to monitor, you don't have to continuously monitor in electrical quantity, right? You don't have to inject a signal to and deteriorate the working of your DER. You can simply, by communication, by interoperability, you can check if your system is working in islanded mode or not. So this is how communication plays a role, but it is still something that people are still researching on, and um, it will soon be uh, a part of detection, islanding based detection mechanism. So up until now, if anyone has doubts, please ask. I'll continue with the protection. Just 10 minutes more, and then we'll start with question answers. Any doubts? So I'm trying to explain most of the stuff. It's just that you can't cover the whole week's lecture in just 2 hours, 1 hour, because I have to complete question answers too. Yes, Dharmendraji.
Sir, power quality issues are mostly due to non-linear devices like power climb
Yes,
devices,
yes,
SMPS, variable
yes,
AC/DC drives,
yes,
and again we control the power quality problems using power climb devices.
yes.
So what I'm understanding that once we create and again we reduce.
Mm-hmm.
Yeah.
Yes,
So,
I'm getting where you are going. But until and unless you create, how will you reduce, right? You have to create something, you have to deteriorate something to be able to check how to remove the deterioration, right? Am I wrong?
yes, sir. Yes, sir.
But tell me one thing, these converters are not so. what happened was you had transformers, right? Transformers are huge devices. I mean, they cover a lot of space, and what they do is they step up the voltage, right? But a converter can do the same thing by modulating the switches in such a way that it can convert AC to AC as well and AC to DC as well, right? But they take only a small part of your space. They are switches, I mean, they are non-linear loads, but what they are doing is they are removing the constraint of your space. And one more thing, how will you convert AC to DC or DC to AC? What are the different ways? There are no ways. A transformer can't do it, right? Because transformer will go into saturation. You can't feed DC to a transformer. It can't work like that. So you need power electronics based devices to be, you need switches. So that's where the switch concept of switch came into picture, right? So what someone did was they had DC. So let's say you had power. I'm not talking about DC power or AC. It's just power, and it's constant for a whole time. What you want to do is you want to reduce this power to a certain level. So what someone did was they started switching it off, then on, then off. So under one cycle, the average was lesser, 50% lesser if you switch at 50% spaces, 50% less than original. So that's where the concept of modulation using switches came into picture, right? So these definitely have issues with power quality, but that's what we are working on, right? Better modulation techniques, better infrastructure, or better equipments could help us answer the power quality issues that they pose. But yeah, until and unless we get a better equipment or a better device apart from them, it would be very difficult, I guess. So it's a research question. It's an open-ended question. I mean, if you're thinking of doing research, there are lots of groups in India who work in power quality issues. Feel free to work on it. I don't do it. I mean, I don't work on power electronics. Anything else? Okay, let's move ahead. So so I'll tell you, a lot of things happen. A lot of inventions, a lot of creations happen by mistake only, right? So so it what we used to do was we used to burn candles, right? We used to burn something to be able to produce light. It only took one creative person in Thomas Alva Edison to think that what can we do instead of burning things? Can we produce light by preventing something from burning, right? He prevented a resistant tungsten wire from burning to be able to produce light. He checked. He thought when you supply AC voltage to a resistance wire, a tungsten wire, you can produce light from it. So it takes one creative person to be able to do something, but yeah, those things should be under our control as well. So until and unless these power electronic device, though they have power quality issues, we don't right now have a better equipment to be able to address these issues as well. Yeah, let's go ahead further if no one has doubts. So when a microgrid which is connected through a PCC, so it is connected to the main grid, right? But what can we do to protect it from faults? So faults can happen at main grid side as well as in the what you say microgrid side, right? And what should be our purpose? What should be our motivation? It should be to clear the fault as soon as it has occurred. So microgrid, we generally use the term for main grid only. It is, since microgrid is miniature size, my macrogrid is the magnified version of this microgrid. So this macrogrid is connected to a PCC at this microgrid, which has some internal fault, right? And it is connected to some priority loads given by these two loads, right? So what we want to do is we want to be able to protect our system from both of these utility and microgrid faults, and we must isolate the system, faulty system, as soon as possible to eliminate the fault, right? And this isolation of the system, or I should say feeder, must be small so that uh, if we by mistake isolate a large feeder, we will isolate uh, what you say, we will isolate loads which were not meant to be isolated, right? So our relays, our protection equipment should be smart enough to quickly isolate the smallest possible section of the feeder. Okay, so how do we do it? So in smart grids, even though we have microgrids, these have these have provided wondrous of opportunities. As I discussed, these have three. I discussed only three. They have many different advantages. One is resiliency, sustainability, and efficiency, right? But they also have some drawbacks. What are they? One, backward power flow, or I should say bidirectional power flow. So this was not the case with the traditional power system, right? You had only power coming from generation side to distribution side. Now distribution is also sending power to the generation side, right? So this has caused our protection systems to evolve now as well, because these have certain issues, which are, so there are differences in the dynamics of the level of power fault currents. There are bidirectional fault current as there is bidirectional fault flow. There is fault stripping and blinding of protection. I'll talk each of these one by one. But these issues should be curbed, and these should be curbed as soon as possible to make our protection system robust to faults. So let's talk what are these individual things, right? So first one is dynamics in level of fault currents. So let's see this small microgrid, right? It's connected to this main grid through this PCC, which is connected to a circuit breaker, this CB1. So I should use this, right? So when a fault occurs, so what happens? It takes power because the fault causes is a minimum impedance path, right? So this minimum impedance path causes current to flow from this faulty section. So the fault current is supplied from the main grid, this uh, distributed generation 1 and distributed generation 2. So the fault current is what? It is the summation of the grid current, the two currents coming from the different distributed generation resources connected to the microgrid. But let's say the PCC is open and you have already designed your relays, and these relays are what? Designed to calculate this fault current. But now, since the microgrid is disconnected from the main grid, you only have two kinds of currents. This is fault current coming from G1 and G2. And the magnitude of this current is less than this current, right? So let me tell this IFA is case A and this is case B, right? Since this magnitude is lesser and your relay was designed to check this current, your dynamics will cause it not to trip while it should trip to isolate this fault, right? So this is one protection issue that is usually that usually arose due to the microgrids. Then you had bidirectional fault current. So what is bidirectional fault currents? Considering the same system, your main grid is connected to a PCC, and let's say there are two different kinds of faults happening. One is this F2 fault, and the other is this F1 fault. This F1 fault is being supplied from G1 and main grid, and this F2 fault is also being supplied from G1 and main grid. Now, now the direction of fault current is also important. The circuit breakers, they sense two currents. One is this IGF1, the capital IGF1 coming from main grid, and one is this uh, IGF2 coming from this smaller DG. So if we take the summation of it, what will it be? It will be the directions are different, but the magnitudes are so it's a vector addition, right? So your magnitude the circuit breaker is sensing will be less. So your circuit breaker should be equipped with relays which can tell if a bidirectional power flow, if a bidirectional current is flowing or not. So that means unidirectional current relays are no more functional in your microgrid protection system, right? then you can have false tripping as well. So how can this false tripping happen? Let's say there are two feeders, and those two feeders are connected to the main grid using relay 1 and relay 2, right? And let's say feeder 2 had a fault. So the fault current for the feeder 2 will be supplied from the main grid and also from the generator connected to the next feeder. Now this relay 1 will sense a faulty current coming to this relay, right? So what will happen? It will trip this feeder 1 as well, and this feeder 2 will also be tripped because of this R2 relay. So false trip has happened. This feeder 1 is a healthy feeder. There was no fault in this feeder, but still the relay tripped. So false tripping is also something that comes due to that is a protection issue with the microgrid. Then there can be one more thing. There can be blinding of the protection in microgrid. What is blinding of the protection? Let's say your utility, sorry, just a second, yeah. So your utility supplies IGF current to this fault, and your G1 is applying IGF current to this fault, right? So, and the relay is connected at the just after the bus of the feeder, which is near to the point of common coupling. So now this relay senses only one current, which is this big current, right? It can't sense this IGF current, first of all. But this IGF, if let's say the G1 wasn't there, if G1 wasn't there, this IGF was greater in magnitude because the fault current is what it is dependent only on the impedance of your the fault, right? So this impedance of the fault is constant. So this IGF earlier stage when there was no G1 connected, G1 not connected, was greater than the fault current when G1 is connected. Why is that? Since IF is constant, it is now being supplied with two currents, which is IGF and small IGF, right? And this IGF will become smaller. So what will happen? Your relay won't be able to sense this current, and your protection will be blinded by a fault. So these are some issues that happen in the smart grid due to microgrids. So there was this yeah, there was this four bus system which was discussed in the slides. SBDR are synchronous based DRs, and IBDRs are inverter based DRs. So all of these, I would request you to first check ma'am's lecture, but I will just skim through these. So when a synchronous based DR supplies fault current, it supplies 5 times the rated current. And due to the internal protection of the power electronic components, it only supplies twice the rated current, right, during fault. Now, how will you measure? So here the fault current is coming 5 times of the rated current. Here the fault current is coming twice the rated current, right? And uh, the main grid is supplying this amount of current to this fault. Now, due to the dynamics, what is happening? So first of all, so can any one of you tell me, due to the dynamics in the level of currents, which one won't be able to sense the fault? Which one is at a at a bad position, at a worse position? So I just discussed, right, how dynamics in the level of currents affects the system. I told you what the current is coming from which part, how the much the quantity is. Okay. Okay. So let's say SBD is connected to the system, right? So this is the amount of current that is uh, being sent by the faulty current, right? So with SBD and without SBD, the fault current is different. So this R5 won't be able to judge the dynamics of the fault level of the fault current, right? So the R5 is at a bad position. So which one will false trip? Because SBDR supplies 5 times the rated current, R3 R3 will be at and R4, right? R3 and R4 will cause false tripping. And third, which one will be blinded by blinding of protection devices? So it would be so since IF coming from the grid is something that causes the blinding, it would be R1 and R6. So I would request you, if you didn't follow this case study, so I have limited time. So you please check ma'am's lecture. So I explained individual components and then I tried building upon it. But if I couldn't tell all of it, you please check ma'am's lecture. But these are some things that causes issues in microgrid. So how do you do it? So you require two different kinds of relays. One is overcurrent relay and one is directional relay. In overcurrent relay, what you do is you check the the magnitude of the faulty current with respect to how it was before tripping, right? And then you check if this is sustained for a particular amount of time. If it is, the relay will trip. And since there is a bidirectional power flow, you also check if a direction using a directional relay, what is the direction of the fault. So how does it do it? You take a polarizing uh, quantity, which is VP. It can be point of common coupling voltage or anything, and then you check the associated fault currents, IF1 and IF2. Let's say IF1 happens, which is leading the VP by 180 degrees. So phi is what? 0 to 180 degree. So if this is the case, your directional relay will tell you that it has happened backwards behind the relay. So this is how the relay is supposed to function. I won't go into the mechanics of it because these are for the next week. And if the phi is between 180 to 160 degree, 360 degree, the fault is ahead of the relay. And what you do is you use both of these relays in tandem, that is, they operate uh, in tandem to each other, that is, they operate with respect to each other to tell what fault has occurred and how to dissociate the fault from the microgrid. And I will tell one kind of overcurrent relay is IDMT relay, which is inverse definite minimum time relay. So what it has is, you have this. This is the amount of fault, let's say IF, and this is time. So as the fault current increases, your time, the time taken to trip the relay also decreases, but it does not go to zero. Even if IF becomes very large, there is still a minimum amount of time it takes. It has to sustain this faulty current to be able to trip, right? So this is a kind of overcurrent relay. Both of them work in tandem to produce results. That is, both of these trip signals are used together to trip a particular circuit breaker, right? So since I have time, um, just a second. Do I have to discuss anything? Yeah. So if anyone has doubts in this protection issues, can let me know. I will be happy to address them. So did everyone follow the different types of faults and how do they affect the protection equipments? I mean, if you don't understand something, don't feel hesitant to tell me. I mean, I will be happy to repeat it once more. Anyone? No one? Okay, so let's move on to questions.
Hello, sir.
So, yeah,
Yeah, sir. I have one doubt.
yeah.
In the next slide.
Next
Yes.
slide.
Here the false. Uh, just go up. Hello.
Yeah.
False tripping in microgrid, right? In this
Hmm.
figure, sir, here R1 come to know that the current is in reverse direction. But how will
Hmm.
R2 know that it has to remove feeder 2 because the current in it is in the same direction?
So you can have, so let's say that's a good question. So I am just uh, talking about what if you use a bidirectional relay, what if you use a unidirectional relay, right? R2 can be a bidirectional relay, it can be a unidirectional relay, and R1 can also be a bidirectional relay or a unidirectional relay. I already told in my previous slide why is it important for a bidirectional relay, because there is a bidirectional fault current, and if the relay is not able to sense this bidirectional fault current, it won't be able to trip appropriately, right? Because what is happening here, the current this current is coming for this fault F2, but it is somehow decreasing the fault current IGF1 because they are opposite to each other, flowing on the same line, right? So if they are flowing on the same line opposite to each other, what will happen? Algebraic sum will be uh, would be subtracted to each other, so the fault it would sense would be less. But is it less? It's not, right? There is a fault in F1 as well, so it should have a bidirectional relay. It should tell if the fault current is coming from this, what is the contribution of it, in spite of having a different direction of fault current coming from the next place as well. So that's where. So let's say we have bidirectional relay employed on R2 and R1 as well. So what will happen now is that if there is a fault in feeder 2, so this G1 will supply this fault current. That's clear, right? And the main grid is also supplying this fault current. So there are two different fault currents. One is the capital GF plus a small Ig1F. Okay, let's say this R1 was also designed to manipulate the dynamics in level of fault current as well, right? What was the dynamics? That if the fault current changes due to islanding, it should be able to tell. So let's say it was able to tell that okay, this is supplying fault current, and since the main grid is supplying power to the fault current, it would supply power to this feeder as well, because it has already found a path of minimum impedance. So the whole current is flowing to the feeder 2. So it will sense this current and it would act as if that fault has occurred in the feeder 1, right? And it can trip. This R1 can trip. I'm not saying it will trip, it can trip. So there can be a false trip, and the healthy feeder is removed in spite of and a healthy feeder is removed in spite of a fault happening in a different feeder. Was I able to tell you? So I was building on different places, right? I started from a bare minimum case where you had simple relays, and then I told how dynamics in fault currents, level of the fault currents affected the performance of this relay. Then we moved on to the bidirectional part of this relay. Then I talked about how having these two as well could cause fault stripping, and then I moved to blinding of the protection in the microgrid. So who was it? Was I able to answer his doubt, or is there a doubt?
Yes, sir. Yes, sir. Thank you.
Okay. Any other doubts? So I would request you to please tell if there are doubts, so that you know this can be an interactive class. I mean, I really like an interactive class. So yeah, let's move on to questions. So the first question we have is uh, a microgrid has an 800 kilowatt load and a 200 kilowatt solar generation capacity. Find the power imbalance when the islanding condition is present. It's very easy, right? What would it be? It would be 800 minus 200. Earlier, this 800 was being supplied from this 200 solar generation as well as 600 kilowatt from main grid, right? Now, this main grid is not there anymore, so the power mismatch will be of 600 kilowatt, right? Next, rate of change of frequency island detection scheme performance is affected by. Can anyone tell me? So, for a Rokov based IDT, what are the factors that affect it? Is it the type of load connected, generator inertia constant, Both of these or none of these? Anyone? No one? I did touch up on when I was no one. So let's say, so what I told you was, so synchronous generators, they have inertia, right? So what is this inertia? Let's say I have to delve into some context that I didn't want to, but let's do it. So let's say this is your 50 hertz frequency, and this is a band in which your frequency should stay, right? And your frequency was working perfectly fine in this band. It was revolving somewhat like this, right? It was in this band. It was working perfectly fine. Being in this band, your system would work perfectly well, right? Let's say at this time instant, a large generator was due to a fault, it was shut down. So what would happen? Since generation has gone less than load, the frequency will dip. So the frequency starts dipping. So this frequency dip is till a certain point before you call your AGC, which increases generations, and then you have tertiary reserves and other stuff, right? So what it does is they start to increase the frequency, and once it's done, it's back into this region. So what you are more concerned is this rate of change. Let's say this rate of change is huge at the beginning time interval itself, right? Then it can be fatal for your system. Why? This is fatal for your system because it can cause cascading of generators. So your generators will cascade into failures and they will go out of sync. So, but how are they protected? They are protected from the inertia. So all the turbines, all the synchronous generators, all the alternators, I should say. Alternators are what? Rotating bodies, right? Rotating mass, we can say. So they have inertia. What inertia does is they curb this Rokov. So they curb this rate of change of frequency so that it will dip, but it will dip slowly. So instead of it dipping fast like this, it dips slowly, right? And this helps in making sure that your performance is not affected. But if you are using Rokov as one of your parameter for islanding detection technique, this can be, what to say? Yeah, this can be your this can cause an effect on your Rokov based islanding detection technique. Similarly, let's say your load is what? It's a PE based load, right? So what does a PE based load do? It is a fast acting load. So if it is a fast acting load, it will react quickly to the change of, let's say, parameters, frequency, voltage, etc. So with a fast acting load, it could affect the rate of change of frequency as well. So your islanding detection technique will definitely see a dip in its performance in these loads as well. So the correct answer is what? Both A and B. So does everyone get it now?
Yes, sir. Actually, I forget the generator concept, inertia concept. That's why.
Okay, okay, no worries. Yeah.
Hello,
So
sir.
yeah.
Yes, sir. I have one doubt, sir.
Yeah.
Sir, in conventional grid, the rotating part is there due to the generators, thermal generators. But when
Mm,
the DRs come into the picture, then
mhm.
the overall rotating part, or we can say inertia, decreases. right? So how we can limit the rate of change of frequency in case of DERs when we have large penetration or large number of
So
DERs?
you have wind is also a DR, right? What do you use in wind? What kind of generator is installed in a wind-based generating system?
So turbines are installed.
So turbines are coupled with what? Turbines are rotating things, right? They are coupled to some generators, right? What are those generators?
Uh, sir, actually, I don't know about that.
Those are synchronous generators. Those are alternators. So what happens is those also have some inertia, right? They are not like they don't have inertia at all. They have some inertia. So and also there is a concept of virtual inertia too. So even in power solar based power plants, you don't operate at MPPT sometimes. You keep a headroom. This headroom is there to affect your frequency. Once it starts dipping, you increase the output from your solar power so that the rate of change of frequency is minimized. So you can have some of inertia by keeping headrooms as well in your DERs. But there are rotating equipments as well. These are called synchronous based DERs. So is it
Yeah, yes, sir.
is it all?
Clear. Thank you.
Yeah, no worries. Next, so ROCPA, which is rate of change of phase angle energy signal, is non-zero for a few samples during non-islanding disturbances. Later, the energy signal reaches to what? This was talked to by ma'am, so I forgot, I think, talk about it. So ROCPA is what? It's your rate of change of difference between phase angle of your voltage and phase angle of your current. So if you monitor this frequency, so this is an index, right? Just a second. Yeah. So yeah, so these are your index, right? So where was I? Yeah. So what happens is so what is an energy signal? So an energy signal is that if you integrate it with respect to time, since this is rate of change of some quantity with respect to time, right? If you integrate this signal with respect to time, you will get a what you say, you will get the energy of the signal. And if you would see in your literature as well, which ma'am told, that during uh, this non-islanding disturbances, what happens is ROCPA based energy signal becomes non-zero for a few samples, and then it reaches to zero because the ROCPA has converged to a particular index. So the correct answer is zero. Yeah, sorry for not covering it, but next, which of the following is not a feature of microgrids? This is a straightforward question, right? Anyone can answer. Yes, someone wrote D. Yes,
Best energy efficiency.
yes. So so it's less energy efficiency. So microgrids are energy efficient. They are able to they are able to yes, it's the so they are able to supply more loads which the conventional grids were not able to do because we have local generations as well during different conditions. Next, failure to detect unintentional islanding events impose which of the following events? This was also talked.
All
Yes. So they can cause malfunction of protective devices, as I told you, and they can cause equipment damage as well, and they can also cause threats to personal or human safety. So the correct answer is all of the above. Next, Rokoff IDT requires a minimum power mismatch of how much?
15%.
Yes, it's 15%. So they have a non-islanding, they have a non-detection zone, and they need at least 15% of power mismatch to occur to be able to tell if an islanding has happened or not. So just a follow-up question: which detection technique is it from? I gave you four different kinds of detection techniques, right? Passive, active, hybrid, and communication. Rokoff-based IDT comes under which umbrella? Just a cross question. I want you all
Passive.
to be on. Yes, passive, because you are trying to monitor a electrical component. Next, in which of the following IDTs is the DR driven to an unstable mode? So we discussed in active techniques. We discussed two techniques, right? One was uh, signal based IDT, and the other was positive feedback based IDT. So which of the following techniques were we deliberately causing our DR go into an unregional operating space? Yeah, anyone? Okay, so in signal based, what we were doing is we were injecting a frequency signal, right? We were injecting a frequency based disturbance, right? But this disturbance was, just a second, let me explain it well. Yes. So we were injecting disturbance, right? But we weren't causing the DR's operation to be unstable. It's just that the disturbance was being passed on to the grid side load or the microgrid side load. If the PCC was not there, it was only till if the PCC was connected, the disturbances were being passed on to the grid side load. While the PCC was not there, it was being passed on to the microgrid side load. But the voltage side, sorry, the microgrid side converter was not experiencing any deliberate unstable operation. But in positive feedback technique, what we do is we deliberately inject a feedback of voltage deviation, frequency deviation, or other stuff to our inverter based resources. So what it does is it causes the DRs to operate in an unstable region, and then the IBR is able to tell, okay, yes, my DR is working in an unstable region, and islanding has definitely occurred. So now, can anyone tell me which of the following IDTs is the DR driven to an unstable mode?
Positive feedback technique.
Yes, positive feedback technique. Because in the current injection or the signal-based injection technique, your disturbance was being passed on to the load. It wasn't being kept to your DER, right? Then voltage unbalance is used to initiate dash method. So we discussed this in what technique? Hybrid techniques, right? So what we did was, so yeah. So we calculated the voltage unbalance, which was the ratio of positive sequence voltages, negative sequence voltage to the positive sequence voltage. And we used it to set up as a set point for frequency of our DG. And we changed the set point frequency of our DG. So what is the set point frequency? Let's say our IBR is working, there is an inverter to connected to our DG, right? So what we do is we change the set point of this IDR, that we tell the inverter to operate at 60 hertz, right? But we deliberately change it to 59 hertz. That's what active islanding detection technique does, right? We change it to a frequency to tell if the unstable operation is occurring or not. So now tell me, what was the voltage unbalance used? It was used to initiate frequency set point method, right? I mean, if you have questions, please ask. I mean, I don't know if you are getting or not. This is hard for me. So, do you want me to repeat it? So So, how many of you did go through the this week's lecture? Just a quick number I want. I mean, it's okay. I mean, I'm not someone who is going to tell NPTEL thing. So, how many of you watched this week's lecture? Because I usually give a disclaimer that these doubt clearing sessions are just uh, supplement to the week's lecture. They add on to this week's lecture. They are not replacement for your week's lecture, right? So you have to go through them to appreciate what is happening in this class. If you don't do it, then you won't get much out of it. I mean, you will definitely get something out of it. You will get a summary, but not too much. So voltage imbalance was used to set a frequency set point for the DG to be able to change how it was working. The next, power line carrier communication uses dash energy communication signal along the power line. So this I didn't talk about. So, when you use a power line carrier communication, what you do is your power line can has a communication system that is a transmission side transmitter and a receiver, which can send signals to check if a circuit breaker is opened or not, and it usually sends a low energy communication signal, because if the communication signal is high, it can cause EMI, which is electromagnetic interference, RFI or EMI with your system. So generally, they send low energy communication signal. Next, which of the following is not a disadvantage of the signal produced by disconnect SPD method? Yeah, this I also talked. So can anyone tell me what kind of transmission interface does signal disconnect method use? Anyone? So So I'm not asking you to, is there any such facility in DRs by which DR owners can supply power to a neighbor, hold a report about this transaction to the ISO if he supplies to a person? What is... Okay, I'll take this question after the class. Sorry, not after the class. I will take this question after these questions. So I just asked one question. In SPD, which is signal disconnect method, what kind of uh, communication link is used? So I talked about it, right?
Sir, microwave link?
Yes. So they use microwave link. So, so this microwave channel is generally expensive. Okay. So this is expensive. Second, since you are using a radio frequency based, you are using a frequency based communication system, you need to license that frequency as well. So you've heard, right? People generally, this 2G, 5G spectrum, right? These are options for different bands of frequencies. So you need to license the frequency to be able to send signals to that frequency. So you have licensing as well. And then you have to design components. So there are design complications as well. So these three are the major disadvantages with your SPD method. Drawbacks, I will write. But what it is not is additional supervision. You don't require supervision, right? Once you install a system, it will communicate. What kind of supervision do you require from your system to do, right? Until unless from a maintenance point of view, you will always require supervision, but not to manually check if the signal is being sent or not. Next, which of the following is our arc protection issues in smart grid? This is a very easy question. I think you should be able to tell.
Is it all?
Yes, all of these. So this is what we talked about here, right? Different kinds of protection issues and how these are being managed in your system. So the relays will delve into further different kinds of relays in the next class, I mean next week. And yeah. So the penetration of DRs not only changes the dash of the fault current. So what is the not only changes? Not only changes. Well, they shouldn't have wrote not only changes. The penetration of DR changes the dash of the fault current. Yeah. Can anyone tell me what is the correct answer? We discussed, right? You can use this as well. So it's both level and
Both.
direction.
Yeah.
Yes. Yeah. Last, the utility grid contribution to the fault current is dash due to the contribution from DG resources. We talked. So if you have a fault, let's say this is your main grid, and you have a fault. Let's say these are two different. So this fault occurred, right? Earlier, this fault current was only due to the current coming. I should draw it from. So earlier, this fault current was only due to the current coming from the main grid, right? So IF was what? IMGF. But if you install DGs, let's say I install DGs, right? These will also supply a part of this fault current, right? So fault current is a constant quantity. It can't change much. So what would happen is this IF will now be IMGF plus the IG1F plus IG2F, right? G1 and G2. So the contribution is reduced of the main grid current. So that's the component, right? Please tell me if you could follow this today's lecture. I mean, I don't know if you could follow or not, but let me give you a brief recap and then there is one more question that I need to answer, right? Which is a, I don't know, very difficult question. So, what we discussed today was we talked about microgrids, how advantageous they are, but still, since these are relatively new technologies, the old technologies that are still there need a replacement. So why? So first of all, they can operate islanding, and if they operate in islanding, there are different issues such as power mismatch, which could cause voltage and frequency to change. So if they change, these are the following different I mean disadvantages that they pose to a microgrid operating in an unintentional islanding event. So then we discussed various islanding detection techniques. There were passive, active, hybrid, and communication based. Then we went on to explore passive islanding detection techniques. Then we delved into active islanding detection techniques, and then we talked about the different drawbacks these two techniques have and how hybrid based islanding detection techniques were able uh, to 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 add to these research gaps, right? Then we talked about one simple hybrid islanding detection techniques and then communication based detection techniques because these are the future of smart grids. Smart grids have to be in there needs to be interoperability, right? And then we discussed how faults in a microgrid could change how we use relays, right? So that's something that we delved into today. Yeah, so one question is there such a facility in DRs by which DR owners can supply power to a neighbor or any other person, not to the grid? Should DR's holder report about this transaction to the ISO if he supplies to a person? So I don't know if someone who is doing research in this area, but yes. So right now research is being focused on peer-to-peer trading. So this DR being able to serve power to neighbors, DRs to DRs. This is called P2P trading or peer-to-peer trading, right? So this P2P trading is something that is being focused on upon because there are different DRs present in the distribution side. Why instead of sending it to the system, they can just communicate with each other, set a price, and then they can do the transaction among themselves. But since they are using wire business from the system operators, right? They need to be able to communicate this to at least the distribution system operator because he is the one who is managing the wire. The wire is what the transmission that these two will be using. And this transmission, so what does a system operator do? System operator checks the power flow in each line and then they compare it with the thermal limit of each line. And if they are more than the thermal limit, it could cause congestion in the power lines, which is bad for the system. If congestion is there, you won't be able to serve a particular load. So these transactions must be checked with the DSO, which is the distribution system operator. To the ISO, no, because independent system operators are managing market at the transmission side, that is generators and discoms. They don't really need to know if peer-to-peer trading is happening. It's only the wire, it's only the business of with the DSO and how it manages the resources that it has. It doesn't need to talk to the ISO to be able to manage these resources. So others, please don't focus on this question. But yeah, if someone has interest in this, I'm happy to help. Yeah, I have one announcement to make. I will be going somewhere next Saturday. So your next class will most probably be on Friday. The exact timing will be conveyed to you by the NPTEL team, and also the link will change. So this won't be the same link that you used today to access the class on the Friday. So I hope I would see good participation from you all. So yeah, tell me if anyone. Yeah, Dharmendra ji.
No, okay, sir. I have noted. Means next Friday we'll
Yeah,
take
yeah.
the class.
Yeah, if you have problems, if you have classes on Fridays or something like that, please tell me. I can shift it to Sundays as well. But I don't want Sunday because I will be in a conference from.
Sir,
So
Friday
I
is
think.
okay, sir. Already 3 classes are going on Sunday, other
Oh,
subjects.
okay. Okay. So Friday, I'll post about it. And yeah, so anyone who has classes on Friday, please let me know so that I can manage it. Okay, so I'm assuming there are no more people who have clashes on that time. But yeah, I'm recording these sessions as well, so you can always take a look at it. So, are there any last few questions? Right, okay, so okay. Any last few questions before I close this class? Any doubts? Were you able to follow today's lecture? It wasn't a lecture, it was a doubt clearing session, but yeah, no questions. Okay, then, so we'll meet next Friday, most probably, and uh, um, then we'll talk about more about these protection schemes, right? So yeah, you can now log off. Thank you. Okay, so I would request all of you to please log off. I need to close this meeting. Yeah. No.